Okay, good afternoon and good evening again. Thank you again for joining this webinar series. So we'd like to start the first webinar. I would like to give a brief overview about this project, and then I would also introduce about some other webinar series that will be in future, and then I would like to introduce also the speaker for today. Just a little bit background. So this is the project that was funded by the California Department of Food and Agriculture from their water use technical assistance program. So our goal was for this project to mostly like provide the technical assistance and also provide the educational as or the workforce development in hydroponic production. Our focus is more on the water and nutrient management for hydroponic production. So there is two part. One is directly work with the growers in California to identify their problem, to improve the water and nutrient efficiency, and then kind of provide the technical assistance to solve the problem. So we are kind of currently working with the growers, identifying the growers to find their problem, and then we'll provide the technical assistance to them for different technology aspect to improve the water and nutrient use efficiency. And the second part of the project is more on the workforce or educational activities. That's the activities that we are trying to do. And we have a couple of webinars that we are planning to organize. So far, we come from 6 webinar, and this is the first webinar. So thank you again for being part of this initiative. I would like to also kind of give an idea. This project is basically in collaboration with UC Davis and the UCANR. Between this partnership, we are working with the hydroponic growers in California. But for educational program, everybody is welcome to join. So this is kind of some upcoming series for the webinar. So today is the first webinar. Dr. Jackson, he will talk about the substrate. Then our next webinars from Professor Neil Madsen from Cornell. He will talk about the how to save the fertilizer and reduce the leaching for container crops. And then the third webinar, Dr. Thakur, he will talk about more on the water harvesting potential for hydroponic production, mostly on the dehumidification aspect. And then Said will talk about mostly on the dosing algorithm aspect, like how efficiently the growers or the production system can do the dosing. Then our next speaker will talk about the light effect on water and nutrient management. And also, so for the out of this confirm webinar, the last one, I will talk about more on the technology aspect, like the advanced sensing technology for hydroponic system. For today, our speaker is Professor Brian Jackson from NC State. He's a professor in the Department of Horticultural Science at NC State, and also he's the director of the Horticultural Substrate Laboratory. He's very well known with the control environment of or the hydroponic community because he mostly work on very innovative aspect like the developing or characterization or utilization of the organic substrate. That is also kind of one of the big concern for hydroponic production, because the traditional substrate has some problem in terms of the carbon footprint. He's mostly working on to develop the innovative substrate to reduce the carbon footprint and also to reduce that to some point the cost compared to the traditional substrate for hydroponic production. So without delaying, I would like to hand over the session to Professor Jackson to start the interesting presentation that we have.
All right, Shamim, thank you very much. Once you close your screen, then I think I can do mine.
You can share now.
There we go. All right, everything look okay on that side, Shamim? I'll take that as a yes. All right. All right. First of all, thank you for the invitation. Certainly, looking at the list of speakers, I'm happy now to be first, based on the speakers that I saw there. And it's always a privilege to speak to a different or a new group. So with the invitation today, I've spent a lot of time kind of putting this together and thinking about this. And when I was asked, as a substrate scientist, we work with a lot of different materials and a lot of different crops and a lot of different cropping systems. So the goal today is to kind of highlight some of the broad, kind of bigger picture opportunities and issues that can be faced with water and nutrient management in growing systems, particularly as it relates just to the substrate itself. So you may have heard the phrase before, dirt, furt, and squirt, where we can't say dirt today since we're using soilless. So we'll just go with a media furt and squirt. So what I'm going to do is provide a little bit of context, a little bit of background relative to the conversation that we'll have today, and then delve into a little bit of substrate physical and hydrological and chemical properties, all of which directly impact water and nutrient management, regardless of what the growing system is. And then we'll delve in specifically to substrate and water usage and how water moves in and out and through substrate and substrate systems. And then also from a fertility perspective, what role different substrates play with fertility management for growers with different crops and cropping systems. And then I'll share with you a few examples of management strategies. I see that the next speaker coming up is doing more on leaching. So fortunately, I didn't talk about that. So that's a good tie-in, I think, to this. And then I'll just share some summary points as I kind of see them moving forward. Now, one thing, if I'm not sure if any of you have ever heard me speak before, but I do pack a lot into a short period of time, okay? And my goal for us today is I cannot answer your specific nutrient questions relative to, why the pH is doing this or a nutrient deficiency in this. I've taken the approach of offering you hopefully ideation, ideas about what you could look at or some of the challenges you may face with whatever system that you're growing in, okay? So one thing that I also like to do when giving talks is to look back. All right. And I often find that by looking back, all right, you can see the future. And this is something that my grandfather and father instilled in me. They'd say, son, how do you know where you're going unless you know where you've been? And I think when you look at the innovation in horticulture across all sectors today, it's very much like this quote, don't look back and ask why, but instead look ahead and ask why not. And that's what I hear so many growers and scientists today talking about with bold ideas that maybe just 10 years ago, 20 years ago, the immediate response would be, no, we can't do that. Now the response from so many is, well, can we? Is it practical? Is it economical? Is it scalable? So there's a lot happening and changing. First of all, let's go back and then look forward. All right. I love the fact that I have been given and I've searched and found a lot of old resources, a lot of photographs that my PhD advisor gave to me from the 1960s and 70s. And to look at where container production and just soilless production of crops is today compared to the 1960s and 70s is absolutely amazing to me. And it just speaks to the innovation. And then fast forward, and we've got, growing plants on moon dust, which shows kind of the cutting edge of what's happening right now. Okay. So in my lab, as Shameen mentioned, here at NC State, the lab was developed in the 1980s. And now I am the director, and my predecessors have all retired. But what we focus on, of course, is all things substrates. We are not a crop or commodity group. I do not study a particular crop. I'm not a strawberry person. I'm not a blueberry person. I'm not a poinsettia person. We study the substrates, how to develop them, how to characterize them, how to formulate them, and then how to match them to these crops and cropping systems as they continue to evolve. And I would also say that we 90% delve into the physical and hydrological side, and also quite a bit of engineering, how to engineer organic materials to create new materials. I'll talk a little bit about that today. But also the chemical and biological. The biological, I do not touch on. That's out of my wheelhouse. It's out of my area of expertise, but it's certainly in much need of development, okay? So before I get into specifics, I do want to take the opportunity to talk to and maybe offer some insights to the holistic approach of where the growing media industry is today. And I think it's always a good thing, hopefully, to get you thinking about. The article on the right that I took a screenshot of was just released yesterday, or I think it was, or maybe Monday. in Greenhouse Grower. And I provided a summary of kind of where I see the tariffs, the trends and trajectories affecting directly the growing media industry. But some of them that we're facing today, all right, peat availability fluctuations. And folks, that has nothing to do with the amount of peat that is available. All right, peat is very, very abundant. All right, but what the fluctuations are primarily related to wet summers and some not ideal harvest seasons that they've had in recent years. This year was pretty good. Actually, I should say last summer was pretty good. Impacts of tariffs. That's a minute by minute situation is what's happening with tariffs and how that's going to impact cost of not just peat coming out of Canada, which we get about 90% of our peat from Canada, but also some coconut products and other materials coming out of Mexico. All right. Increased demand. I won't get into that too much, but some of you may have heard the statistics that the projected forecast of soilless growing media between now and 2050 is to increase by over 400%. And a lot of that is in response to more production area, all right, of controlled environment systems and outdoor container production areas. But it's also increasing competition from new crops that are now being grown in soilless at rates and acreage that we've never seen before, primarily with soft fruit. And those fruit and those new emerging crops in soilless systems rely on the same substrates that we have in the ornamental world for the last 60, 70 years. There's also a tremendous increased interest in domestic substrate production, and there's a lot of reasons why. I will not get into all of them, but there's a lot of emphasis and funding now to identify and to create and market and transport and commercialize domestic substrates to supplement, all right, our peat coming from our great neighbors to the north. And then also an emphasis on more renewable materials that are locally or regionally available across the country. So that's kind of an overview of kind of the substrate industry right now. Okay, so obviously this is the CEA series, but I do not know where all the viewers either now live or who will view this at any point in the future. You know, there's growers who are using high tunnels. There are growers that are nursery outdoor production of fruits or ornamentals. There's hoop houses and high tunnels and greenhouses and vertical farms. And you think about it, you know, everything is protected in some way unless it's a truly outdoor nursery production. So the goal of today is to kind of hit on topics that would fit any of these systems, okay? Not one in particular, all right? So think about the function of substrate, and this is something that was taught to me by my predecessor, Dr. Bill Fontenot. He said, Brian, a substrate does four things. There's support, there's air, there's water, and nutrition. All right, but then he said very clearly the substrate only does one of those things, and that's offer support for the plant. The grower is responsible for the nutrition, air, and water. And folks, that all comes down to management. So that's what we're going to talk a lot about today is just in the management of those three key components relative to crop production. All right, let's start with a little bit of physical properties and hydrological properties of substrates and how that directly pertains to irrigation management, all right, water capture, water loss, water fate, as it relates to crops and crop cycles, all right? One thing to impress upon you, right? The physical properties, all right, of a mix do not come from the substrate components. The overall end physical properties of a mix do not come from the substrate components themselves, all right? Instead, those components create the physical properties, as does the filling process and the container itself. And we're going to talk about these. The substrate physical and hydrological properties are highly manipulatable, all right? They can be manipulated in many different ways, all right? So as far as physicals go, there's four basic ones that we look at. All right, total porosity, which of course is made up of container capacity, total amount of water, and then the airspace on a volume basis within a container or some type of growing system. And then of course the bulk density, how much mass is there per unit volume. And our lab does a lot of testing of physical properties to characterize and to compare things to each other. And even looking in this photo, from slabs of rock wool to peat to coconut, and all of these different materials can have very, very different physical properties. All right. Now, to put that in perspective, we're going to talk a lot today about pore space, porosity and what that means relative to management. So thinking about a mineral soil, all right? A mineral soil on a volume basis is 50% solids, okay? 50% baby rocks, all right? Weathered rocks. The other 50% on a volume basis is just the pore space. It's the air and the water. But substrates are very different. Soilless media have almost no or little actual solids. Instead, it's all the spaces. And what that space does is brilliant because it allows us to manage these mixes very well. All right. I'm going to share with you a bit later a little bit more about tomography, some work we did in the past where we took X-ray tomography and we actually did some work on different substrates to look inside, literally as a plant root would, and to look at what the pores look like, look where water is. And through the software engineering of this tomography, we can kind of map the pores. And the photo on the left is from a peat sample to give you an idea of really what a root sees. So really, there's a lot more pores than there are solid particles within any substrate. This is another example to kind of give you a bird's eye view, or should I say a root's hair view of what it looks like to grow through a substrate. And what these are, three different types of peat moss. On the left is a blonde peat, newer, closer to the top of a bog. And then you've got brown peat and then black peat on the far right, which is further in the bog, further decayed, a higher bulk density, and very different characteristically than the blonde peat on the far left, which is very young. All right. So using these technologies, we can understand more about these pore structures and the overall substrate properties. All right, I wanted to start kind of here when we talk about physicals, because this is something I see so much from growers who use peat perlite mixes or coconut perlite mixes that add perlite, automatically assuming that the addition of perlite improves or increases porosity, particularly airspace. All right, and more often than not, I have found that that is not the case. Okay, and by the way, this talk is not going to be very data heavy, but I'm going to show you some to illustrate some points and some concepts. All right, so on this graph, what we have is total porosity on the left. All right, and we've got pure peat. The first bar is pure peat moss, and the solid blue is water, and the little gray box at the top is the airspace in that peat. Okay, so for this peat sample that I analyzed, it has 80% water and about 14% airspace. Now to that, the second bar is 20% perlite added to that same peat. The airspace barely went down at all. Statistically, probably not even different, but realistically is more importantly, it's no different. And then even at 40%, very little drop in airspace. And it wasn't until you get to 60 or 80% perlite that you start to see a real rapid shift change in the porosity, the airspace. Okay? So what that is what I call the hockey stick effect, where you basically have amendment after amendment and it just kind of flatlines, nothing happens, and then there's a threshold where 1% more or 5% more really escalates the change that you're looking for, okay? Let me show that to you in a bit different perspective, okay? And maybe look at your own mixes, certainly if you make your own, all right? Let's look at these two peat materials, okay? On the left top, I'm sorry, on the right top is a Canadian peat, really a milled peat, finer grade. And on the bottom is a coarser, chunkier peat, more European style. And then we've got all of these different particle sizes of perlite, okay? Let me try to illustrate this to prove my point. Just because you add perlite does not automatically assume you're going to increase airspace. Because if you, for example, add that particle size perlite, all right, on the bottom right of this photograph, to that coarse peat, you're not going to increase airspace, you're going to decrease it and increase the water holding because the particles of that perlite are so much finer than the coarse pores and particles of the peat. On the contrary, if you take the coarser perlite and add it to the finer peat, now you're getting the result that you likely wanted, where you actually do get a more drastic increase in airspace even at lower percentages of particles, of aggregates, in this case, perlite. All right, let's talk about hydration and specifically as it relates to water. And I'll go through a few concepts and a little bit of data point to understand just how substrates are different, all right, in hydration, and then what that means from a grower's perspective as far as irrigation and water, okay? So we've got several things that we measure. Wettability, okay? How hydrophobic or hydrophilic is a substrate? How easily does it take up water, okay? And then we've got capillarity. We do a lot of capillarity work where it's basically mimicking ebb and flood systems, all right, or sub-irrigation that water has to pull, excuse me, substrates have to pull the water up against gravity, all right, as opposed to overhead irrigation, which relies on gravity to pull it through the container. All right, then we have container capacity, the total amount of water that a given substrate can hold against after gravity has drained all the water it can, all right? And then we have the effects of initial moisture content. You're going to hear that repeatedly in the next few minutes as the initial moisture content at the time of potting or at the time of transplanting or at the time of the first irrigation is a critical step in ensuring that you get your substrate, your container, the entire root zone volume wet really quickly. And then, of course, the hydrophobicity or hydrophilicity that can be measured with any of these testing parameters. All right, let me give you one quick example of wettability. All right, and this is where we simulated irrigation from above. Okay, now what we did is took pure peat moss, all right, and we took a sample at 25% moisture. All right, and that's similar to what you may get peat moss if you have one of those the smaller compressed bales or even the towers. You open it up, and sometimes the moisture is around 25%. It's fairly dry. Okay, so on this graph, all right, the solid line. Let's look at the solid blue line first, right here about the 25% level. The solid blue line is pure peat without a wetting agent. That's as much water as it can possibly hold. Only about 25%, okay? Now, all of these other lines closer to the top, up here showing about 70-75% volumetric water content, the yellow, the green, and the red lines, those are all the maximum water holding capacity of that peat with wetting agents added to them, okay? So in this wettability system, we took a sample of peat and we flushed water. We ran water through it, all right, systematically through 10, and we simulated 10 different irrigation events. And here on the x-axis is 10 different irrigation events. All right. So now we've got the green line with the triangles is a low rate of wetting agent, and then the red line with the X is the medium rate of wetting agent, and then the orange line with the square boxes is high wetting agent. All right. What do you notice? All right. None of the treatments, not even the high rate of wetting agent, can fully wet peat to that solid line above. Okay. That is how drastic really dry hydrophobic peat can be. All right. Now, let's take it one step further. Peat increased moisture to 50% with the same levels of wetting agent added. And look at the blue line below. That's the peat with no wetting agent. And after 10 irrigations, it got up to 40% water holding. But all the others, after just one irrigation, despite the presence of surfactant, a wetting agent, immediately got to their maximum container capacity and they were fully wet even after the first event. Folks, the initial moisture content is critical at the time of potting up. Okay? So, next, ebb and flow or sub-irrigation. All right, now to remind you, looking at this graph, surface irrigation here on the left uses gravity, all right, just to pull the water through the container and it wets the substrate laterally and vertically as it goes down, all right? But sub-irrigation relies on more exclusively relies on capillary action where the water's coming from the bottom and it has to pull the water up against gravity. Okay, it's a much different challenge, and some substrates do that better than others, all right? So let me show you really quickly a comparison between the same substrate that was irrigated from the top down and from the bottom up, all right? And I just chose to use peat moss, and we did it at 3 different initial moisture contents, okay? So peat on the left at 33%, and then the middle was 50%, and then peat at the far right is at 67%. Pretty moist at the time of potting, okay? Now, looking at each graph, the blue line represents the surface irrigation. And then the orange line represents the capillary rise from the sub-irrigation. What you see at all moisture contents is that the surface irrigation thoroughly wets more thoroughly wets the substrate contents of the container compared to subsurface. All right. But what you also see is that as moisture content increases from 33 to 50 to 67, that even the surface capillary movement of water is greatly impacted. Okay. We'll talk a bit more about this later as it relates to container height and sub-irrigation. There's a balance there. You can't get too tall of containers when you're sub-irrigating. All right, so just some few general principles relative to water, water, water. All right, hydrating substrates prior to pot filling and at transplanting or at seeding. All right, if you're direct seeding, lettuce or something direct seed. All right, is the best way to ensure a full hydration in minimum irrigation events. All right, you don't want to have to irrigate something 13 times to be certain that it's actually wet and that young transplant or seed is actually moistened. All right, the second thing, irrigating based on plant need reduces extreme drought. We'll talk about that a little bit later, but just irrigating based on what the plant needs when it needs it, which, as you know, depends on the growth stage of the plant and a lot of other variables. We'll touch on those in just a few minutes. And I am a big fan of surfactants. All right, yes, it's an added cost, but it is a great insurance policy in the event that the irrigation doesn't run a cycle or two and it starts to dry out or any other issues. So surfactants are really, really, I think, beneficial. And I show the images here, adding water on this mix line on the far left at the time the substrates are made. And then once they're potted up, there they are with going under the water again. Of course, you add water when you grow. And here on the far right is what's often done with a lot of greenhouse foliage crops and bedding plants is they're watered really thoroughly before they get on the truck to go to the garden center or the retail center. All right, so watering at all of these stages. All right, let's talk a bit more specifically about water and where it goes and how it moves. Okay, so thinking of water management specifically, well, first and foremost, all right, it varies by crop and crop growth stage. Okay, me not knowing and having no way of knowing, you as the viewer, what crop you grow, what system you have, are you indoors, outdoors, high tech, low tech, all of those things, of course, vary relative to how you manage your water. Of course, it varies by substrate. We just talked about different hydration properties that different substrates have. It varies by container systems. If you're in a gutter system growing lettuce, if you're in a trough system growing strawberries, if you're in a lay flat grow bag growing, cucumbers, all those factors change. And then a time of the year, of course. All right, the warmer it is, the hotter it is, the more sun exposure. Of course, you've got more water evaporation and water loss. All right. So what happens if you manage well? What happens if you manage your water well? All right. Well, one, you can control the growth rate. All right. Again, we're growing in mixes that are mostly all pore space, air and water. All right. And we can manipulate that. That's what makes us precision growers. I should say you all. I only grow research plants, but you control growth rate. With water, you can more easily control the finish size of your crop. Certainly very important for something like poinsettias or mums or a lot of plants that are very height specific at certain points of their finish time. Reducing disease threats by not keeping the substrate too wet, of course, for the root-borne diseases and pathogens. And then I also once again here mention considering surfactants, all right? And you can get granular or liquid added directly to the substrates as they're being formulated, all right? Or you can also inject certain surfactants directly into your irrigation water as well for that, all right? Now, here's an important point. At least I think it is, and something that I've learned on the research side, working with other colleagues on the same crop, but in different growing systems. And this is something that seems pretty intuitive, but it is very, very true and oftentimes maybe not considered. Certainly for growers who may have more than one type of growing system for the same crop that they are using, okay? So the same substrate, the same crop, in this case I use strawberry, the same irrigation delivery method and same water source, in different growing systems will have very different water needs. And whether that's outdoors, in a high tunnel, in a greenhouse, or in a vertical farm, or vertical chamber, all right, it's the environmental parameters of those spaces or around those plants that are pulling more water or not, all right, in addition to the plant growth itself. So if you have the same substrate growing the same crop in different systems, you can't use the same management strategy throughout the entire cycle of that crop. Of course, irrigation delivery method. I mentioned that when we talked about wettability and capillary movement of water. All right. But you've got overhead irrigation, certainly like in an outdoor nursery setting when you've got overhead sprinklers. You've got drip or surface application, and that's true in a lot of greenhouses. It's certainly true for lettuce and a lot of higher tech CEA growing of leafy greens. Then you've got a lot of flood sub-irrigation. All of those things factor in as well. And you can choose, or maybe with the help of your substrate supplier, a better mix that is better suited for your particular irrigation delivery method. Okay, so let the substrate cater to your existing system as opposed to the other way around. The other thing to think about as far as substrates and the container that it's in as it relates to water, okay? Well, let's think first about plastic versus non-plastic pots, okay? Well, plastic pots, of course, do not allow water to evaporate through the sides, but these peat pots and coconut pots and fiber pots and all of these non-plastic alternatives, they're breathable, all right? Water can move through the side. Therefore, it's going to dry out a lot faster compared to how you manage a crop in the same size pot, but being one that's plastic, okay? The other thing, a solid plastic container versus some of these newer, well, I say newer, they've been around for quite a while, the Pioneer pot or the air pots that expose a lot of air to the entire substrate surface through these openings. Of course, that's going to drastically impact how the water not only is moving through the substrate, but how quickly it dries. All right, how about substrates and the irrigation system and the container? Now talking about the crop. All crops, don't grow the same way. And if you travel to Europe much, you go to greenhouses and you may walk into a greenhouse that's 10 acres in size and they only grow cyclamen or they only grow orchids. All right. Well, here in the United States, you walk into a typical 10-acre greenhouse and there may be 200 or 300 different varieties of plants and they don't all have the same watering needs. All right. So thinking of matching a substrate to a crop, well, what is the crop's water needs? What are its air needs? All right, fertility. They're heavy feeders, they're light feeders, and that, of course, plays from a fertility perspective how you have to manage individual species. You have some that are more sensitive to others. Now, sensitive, primarily as it means, higher EC or higher salt is going to burn them. There are also sensitivities to phytotoxic compounds that can be in some mostly organic substrates. We'll talk about that in a few minutes, but that crop sensitivity to some chemistries and phytotoxins is really key. And then how long is it going to be in the container? If you're growing like the middle photo in the top, if you're growing a watermelon transplant, all right, for a matter of weeks, all right, it's a very different setup than in the bottom right if you're growing blueberries for multiple years. So the length of crop cycle or life in a pot, how many birthdays is it having? That really drastically impacts the crop substrate container selection. All right. As far as measuring water. Now, this is by no means my expertise in the production side of things. There are many others who are experts in novel sensor and other technologies for monitoring and measuring water in systems. All right, but the most precise is gravimetric. Okay, because 1 milliliter of water weighs 1 gram. So when you put a pot on a scale and you watch the numbers click down, 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 quantify exactly how much water it's losing and when to re-water. And there's some parameters about how to do that. There's also all types of moisture sensors, as indicated here in the top right photo in this pot and pot system, but a lot of smaller moisture sensors that are used in containers and container systems. And then you've got the eye test. All right, where you're looking at the crop, you're looking at the color of the substrate surface. Does it look like it needs water? And then there's the muscle memory. All right, you know what the pot should feel like if it's fully wet, and you walk by and you pick up a few. Oh, okay, it kind of needs water. There's still a lot of growers who do that. So those are kind of the four main ways of measuring and monitoring water. Now let's think about container height as it relates to water, just water and air. Okay, and most of you likely know this. All right, the same substrate in these three different containers, all right, are going to have very different air and water percentages based on the height of the container. All right, so the shorter the container, the less it drains. So the strawberry here on the far left, look at the percent volume in this illustration of that root zone that is in water, okay, compared to the very taller pot the amount of water, the root zone or the perch water table doesn't change, but what does is the airspace at the top. So the taller the container, the more it drains, the more air it has, even with the exact same substrate in all three of these, okay? Now that's very important when we think about matching substrates to containers. Now folks, this is something that my predecessor has done for before he retired for decades, and we're still doing it at NC State. We have the ability to run analysis, generate data on the physical and hydrological properties of substrates, and then we measure the geometry of different containers and container systems. And then there's a model that we can plug these data into, and it will forecast what the air and water percentages are in any substrate in any single container, regardless of size. It can be a 288 cell plug flat, or we could model a football stadium and tell you what the air and the water balance is, okay? Now, don't freak out with that big table. Let me just kind of walk you through this, all right? So what we have at the top, these are container sizes, okay? So where, if you can see my mouse, that's a 3-inch core, which is what we measure physical properties in. Imagine that as a 3-inch pot. 4-inch pot, 6-inch pot, 8-inch, 1 gallon, and a 2 gallon, okay? Now what these are, forest gold, green fiber, and hammer milled PTS, those are just different types of wood fiber, wood products, which is kind of been my thing for about 20 years now. Let me show you differences, all right? Now the red boxes I just shown are container capacity, all right? Well, let's look at this 3-inch core. 20%, all right, here on the left, 20% of this wood amended to peat has a 68% container capacity, but in a 2-gallon pot, that drops to 52. It drops 16%. Oh, well, what happens to air? Well, the exact opposite. At this 20%, airspace is about 11%, but in a 2-gallon pot, it's almost 27%. So we can do all of this type of work without actually having to test substrates in all of these individual containers. So it's a pretty neat system. One more quick example, all right? European peat. We get a lot of European peat shipped over from our European friends, and of course, Canadian peat. Very different in structure, most usually. Well, let's take a look at those same data, all right? And I can't show you just based on how I cropped the table. I can't show you, but these are all the same container sizes I just showed you earlier. And look at the Euro peat, all right? The coarser peat here has a 23.9% water holding, the Canadian peat 6.4. All right. And then you can see all the way across the difference between those two peats in different container sizes. So if anyone ever says peat is peat is peat, they clearly don't know what they're talking about. They're very, very different materials based on particle size. All right. So a project we just finished up about a year ago with a former graduate student of mine. We sourced 30 different containers, ranging from germination propagation size containers to lay flat grow bags and troughs, more for berries and greenhouse vegetables, all the way up to large grow bags and large containers. All right. And we mapped and we modeled all of those containers through dozens of different substrates to get an idea to provide growers with, hey, here's my substrate, or here's the pot that I have. Which one of these substrates may give me air and water like I like? One other thing we can do with this type of work, here's a lay flat grow bag, and we can actually measure and calculate how much water is in the top of a lay flat grow bag versus how much is centimeter by centimeter all the way to the bottom, and we see how much actual water is being held. So those are some of the more high-tech, I say, things that we're doing, but just to understand air and water in a container. Now let's think about where water goes, all right? Well, the fate of water. It's going to evapotranspirate through the leaves. It's going to surface evaporate. It can go through the side of containers if they're porous containers, or it can leach out, all right? Water can go in a lot of different directions. So one thing that is often done, and we do it in our lab, we have this load cell or these lysimeters in my greenhouse, and each of these is an independent scale, and we can weigh plants over time to see how much moisture they're losing. A similar approach to the gravimetric way of monitoring moisture loss in a production area, as we talked about a few minutes ago. One quick thing just to kind of illustrate that not all substrates are the same. Folks, this is peat particle size and water loss over time. All right. And our peat particle size, the blue line is 3 millimeter in size, and then 2 millimeters and 1 millimeter. And over time, all right, 8 days, there's a 36% difference in the 3 millimeter versus the 1 millimeter. Particle size matters relative to how quickly substrates dry out. All right. Now, one other example to show a contrast. This is wood particle size. You know, I mentioned I do a lot with wood products. Wood products, exact same 1, 2, 3 millimeters, and there is virtually no difference in how they dry. Different materials dry differently. The other thing we can do with this system is to actually grow plants and put them on and actually calculate how long it takes them to wilt. All right. And then how do we mitigate that? By doing something to the substrate to increase the time it takes to wilt. And this, ladies and gentlemen, is more focused on post-production. If you're growing container plants in your greenhouse, in your system, that's great. You know how to do that. But once they go out to the retail, they're on their own, so to speak. So how do we improve that post-harvest shelf life? The other thing, thinking of water and evaporation, oftentimes mixes will dry differently on the surface. And in particular, this is true for wood substrates or substrates that contain wood fiber above 20%. And you can see on this photo on the left, see this dry crusting? It looks like it needs water. All right, well, you take that pot off and look at the bottom, and you quickly realize it doesn't. Folks, of all the growers that have transitioned over to some percent wood fiber, engineered wood fiber in their mixes, the adjustment to irrigation management has been almost unanimously the number one issue they've stated was the biggest thing to overcome for them as growers to learn how to grow in new mixes. It's water management, not pH for fertility or other things, it's water management. And as one quick example, on the photo on the right, this is pure peat moss on the top, and I added 20 and 40% perlite. And then these are 3 different types of wood, and I added the same percentages, fully wet them, 24 hours came back, and look at the peat at the top. Zero difference in color, looks the exact same, but I think you can visually see the difference in the wood products. That's that eye test does not work when using some of these wood mixes. All right, I told you we'd go back really quickly to look at tomography, all right, the X-ray stuff. All right, let's look at where water is even in plugs for propagation. All right, this is before irrigation, this is after. And now we can look at different propagation substrates, whether it's foam, whether it's loose field substrates, whether it's gels, whatever it is, and see where the water actually is and then how to improve that if we wanted. Also, look at water in containers. This is pine bark in a container before irrigation and after. We can see where that water is distributed and not just see for the hell of looking at it, but then how do we alter where that water is? How do we change that some way? That's the real fun part, all right? And I just wanted to show and give credit to some additional work that Paul Fisher at the University of Florida and James Altland at USDA also have done with tomography, looking at young plant plug production and air and water values, all right, using the same technology. All right, well, let's talk about how do we keep water in the pot. And folks, I only chose one method to show you today. There's others that we and other scientists and growers have come up with for how to increase the amount of water in a container. But something I have seen dating back to 2018 at my first visit to IP in Essen, Germany in January. And I saw this material called a pot cover or container mulch. Now, I'm very familiar with container mulching in outdoor nurseries, ornamental nurseries, because they do it for weed control. It's a great weed control measure. But they're doing it in Europe as a top dressing of the containers from a water conservation perspective. And they're getting some really interesting data. And we've picked up this research as well in my lab to look at what is the water usage during production with covering the surface versus not. And also going back to that post-harvest shelf life and wilt time, by covering the container before it goes to retail, what does that do to the wilt time? All right. Well, these are 5 products actually, that I know are on the market in Europe. All right. Klassmann has one that I'll show you a bit more of in a second, but there's several of these container top mulching, horticover top dressing materials. I say I'm excited about this, all right, for the North American market, if it's feasible based on what the growers think. Just specifically to Klassmann, they have an excellent website with their container mulch. And with that, they show this. They show 3-liter containers of plants that were grown, put on scales, and the yellow line is the containers without the container mulch, and then the red line is the containers with, I'm sorry, the yellow line is with container mulch, and the red line is without. And then look at the weight difference between with and without, all right? That would drastically increase or increase the amount of time to wilt. So something to think about. All right, substrate chemical properties. All right. Now, chemical properties, unlike physical properties, do come with substrate components. All right. You've got the initial pH of the substrate itself, as well as the buffering capacity of the pH. You've got electrical conductivity, the EC, of course, cation exchange capacity. We'll talk about that more in just a second. Residual fertilizer salts if someone is reusing a mix. That's a topic for a different day. All right. There's also phytotoxins. I mentioned those. And then heavy metals. Now on the bottom right, this is an apparatus called an XRF gun, and they're not cheap, but they are available. And you can literally put that on a soil or a bag of mulch or bag of potting soil, press the button, and it will give you the readings of all the heavy metals. Okay, so there is a way of testing for that. Now, I do want to highlight just for a quick second these two particular properties. All right. Now, cation exchange capacity. If you've taken soil science or you've talked much about soils, this comes up pretty quickly. What is its relevance? Is it important? And my answer is absolutely if you're growing outdoors in the field, or if you're growing at a nursery, outdoor ornamental nursery or small fruit, are completely exposed to the elements, yes, it helps to hold nutrients. All right. And tradition tells us that substrates also need high CEC, right? Even for very high-tech controlled CEA systems. All right. I don't buy it. Okay. And here's why I say that. In controlled protected cultivation, low or no EC is often desired, even by substrate manufacturers. They don't want a lot of salts and nutrients already packed in there, nor do they want the substrate to be able to hold a lot. Why? That reduces our management capabilities if you can't get the nutrients out. All right. So why is this? I say how to pamper plants. Well, you grow it in CEA because we are dosing on drip by drip all the water they need to stay happy. Oh, the fertilizer's low. Let's pick it up a few part per million. Oh, you need this. Let's do this. Oh, you need this. And then the water that drains out of the bottom with nutrients is often recaptured, all right, and then reused. It's not a waste or a pollutant. So CEC in these type of systems is not something that I even consider. All right. Now this is a lot. I'm not going to go through all of this much, but basically the premise is this. All right. Growing plants in these high porosity growing media is more like growing plants in water and air than it is compared to growing plants outdoor in the soil that have to fight their way through 50% baby rocks and a little bit of porosity. Okay. So these inert substrates with very low or no CEC, they can't hold water, or they can't hold nutrients. So it's less likely to accumulate fertilizer and salts, which can be a problem. That, however, may mean that they need to have more nutrient renewal every irrigation, okay? Fertigation as opposed to dose irrigation for fertility. And the inert substrates have minimal effect on pH relative to organics with high CEC. Therefore, you really have to monitor the pH very, very closely. And rock wool, stone wools, and perlite are two key examples of inert substrates used heavily in the hydroponic world. And then a quick note about phytotoxicity and why this matters. More so if you are making your own substrates from materials that you're getting locally or that you have on site. All right, be very careful with some of these organics because phytotoxicity is any substance in the soil, in the substrate that can inflict a negative response to plant growth and development. And this is really noticeable on fresh or green organic materials, particularly wood. All right. Now, not all the commercial wood fibers on the market have phytotoxicity. Okay. They've been intentionally taken out. But if you use fresh sawdust, expect major, major phytotoxicities. And there's ways in which to test for that, but that is something that causes a lot of sensitivity in plants. So as we say in my lab, if we can smell it, the roots can taste it. Okay. And that's a good idea for pine or other materials. Even compost, you can smell if it's rank or not. It should smell like almost nothing, okay? All right, media and water testing. Just a note, just a little blurb here. Physical and hydrological, you can send it to a lot of testing labs to get a porosity and container and airspace. You may also want a particle size analysis to look at the particles that you have and maybe increase those particles. And there are, I think, some labs that do that. For chemical or nutritional, also sending it to any of the testing labs. I want to mention pre-plant and post-plant pH and EC for a second, all right? When you pre-plant pH, you're blending your substrate yourself or your substrate comes in from your supplier, okay? Well, the two methods to really adequately or accurately test your pH is the 2 to 1, right? 2 parts water to 1 part substrate, or a SME, the saturated media extract. Okay, those are 2 easy tests. 2 to 1 is very easy. Now, post plant in production, all right, certainly if you're growing in containers, the pour through method is the best, is the easiest one for actually measuring that. All right. Now, just a few points about crop fertility. Okay. And not a whole lot. I can't answer all the questions about fertility for that, but let's highlight a few things. First of all, we talked about pH. All right. General pH range, and this is old school. I know 5 to 6.5, and that's certainly very crop specific. And pH can be altered by the substrate, the fertilizer, the water source and type, as well as the plant. And one note, all right, if you're growing in any peat reduced materials, or if you're transitioning away from rock wool or perlite, or if you're transitioning at all from what you're used to doing, really pay close attention to the pH, because all the pH in these materials is not the same. And if you're blending yourself, really be careful of pre-plant lime additions so you don't start with a pH that's too high. All right, the other just general recommendations, all right, pretty straightforward as far as fertility management is based on the substrate you use. All right, the growing system, indoors or outdoors, the crop, of course, the growing season and the weather, temperature affects a lot of nutrient release and use. Pre-plant fertilization, either in starter charges for mixes that you're buying in or young seedling mixes, or if you're doing controlled release incorporation prior to planting. Then you got post-plant fertilization, usually water soluble, either constant feed at a lower part per million every irrigation, or a scheduled fertilization where it's a higher part per million, and then you have intermittent irrigations of clear water. All right, monitor EC routinely, not just when you see issues. All right, because it's, as my PhD advisor used to say, it's easier to add more than it is to take it away, like this little photo here on the right. All right. Real quick, people ask me a lot about organic materials and nutrient tie-up. Okay, nitrogen mobilization or nutrient tie-up is just when microbes are eating that inorganic nitrogen or nutrient, and when they take it out of the substrate system, the plant doesn't get it. So you have to jack up the fertilizer rate for the plant to have its optimal fertilizer. And there are a lot of things that affect immobilization. All right. Composition of the material, the C to N ratio, particle size. I show the images on the right just to show some of the different particle sizes of the common organic materials that are used. The smaller the size, the greater microbial activity, the higher the draw of nitrogen out of the system. And then, of course, temperature and moisture. And a greenhouse is perfect. So a lot of nutrients are tied up in that. And I doubt, if you're really, CEA, you may not use much bark, but outdoor production, there's some bark in a lot of greenhouse mixes. I get this question a lot too. Well, bark, you can't use it fresh. It's got to be composted, all right? Because it's going to tie up all of your nitrogen. All right. Well, folks, I have dug through the literature for the last 20 years, and there's only like 7 or 8 papers and even like grower reports. And of all the work, none of them have really said that nitrogen is the limiting factor in fresh bark. All right, really none of them. The growth differences in fresh bark have been attributed to available water in the fresh bark being different than aged or composted bark, and or phytotoxicity. Okay, so bark really doesn't do very much. Wood substrates, and this is 100% wood. Now, this is far left field. No one's doing this, at least yet, but I just wanted to share this with you here at the end to show that a lot of work has been done to calculate how much fertilizer can we add or do we have to add if we wanted to grow in very high wood mixes. And repeatedly, about 100 part per million nitrogen is needed over the crop cycle compared to a peat mix. All right. If you're using any engineered fiber in whether it's lettuce, whether it's ornamentals or floral crops, 20% fiber or less, wood fiber or less in peat really has no impact. Okay. You get above 30 or 40% and it could be a draw. All right. So just monitor those ECs. The other thing, really, the only last point I'll make about nutrition is sulfur. If you're growing crops in 100% wood, and while that's not happening much, I see it coming sooner than later in lay flat grow bags for a lot of vegetable production in greenhouses, maybe even cannabis production. And if they're going to grow in 100% wood, they need to have a sulfur source. If the sulfur source is not in the water, all right, at least 15 parts per million, then you add a pound of gypsum per cubic yard, just calcium sulfate, and it resolves that sulfur deficiency in crops. And we looked at 5 different sulfur sources and easily determined how to get rid of sulfur deficiency. Okay, I'm not going to go through all of these, okay, because you can look these up as far as all of their individual properties, chemistry, hydrology, physicals, but peat moss, coconut coir bark, and wood fiber. Biochar is kind of entering the field, trying to anyway, if the cost can come down. And then organics, and Shamim, I'm almost done. And then organics, perlite, and rock wool, of course, are the 2 most important in the hydroponic system, but there's a lot out there. So in wrapping up, a few quick innovations, all right? I do want to mention stratified substrates, the layering of different components on top of each other, a concept that colleagues of mine had nothing to do with it, but Jeb Fields and Jim Owen, and stratifying, putting coarser on the bottom of a pot and finer on the top, does a better distribution of nutrient water balance and efficiency in containers. And we've also seen that you can layer or stratify cheaper materials on the bottom of a container, use a more expensive peat on the top, and reduce peat usage. And Jeb Fields and his students have shown that in young plant production, and we've done it here with both poinsettias and strawberries. All right, imitation or flattery is the best form of imitation, or imitation is the best form of flattery. This is some stratified with miscanthus out of Wageningen University. All right, so there's a couple of products. You know, there's biochar now on the market. There's a lot of peat reduction happening for out of choice. Some growers are choosing to do that, so the industry is responding. Product innovation. Oh my goodness, with the CEA world, with stabilized plugs, polymers, gels, you know, the Grow-Kun and Klossman is doing a lot. Bio paper, Grow Cup, Phyto plugs. There's on and on. All of this aimed at the CEA market. So you've got a lot more options today. So as I finish up, you have to always think your funding sources. And one thing I'm always proud of is that the commodity groups and the public and private sector is really funding a lot of substrate research. And we're excited about what the next few years has to say. Always additional resources. There's books, there's websites, there's extension publications that can answer your specific questions. So my final thought, substrate, container, water, fertilizer, plant interaction. You got to consider all of those, all right? Otherwise, you may have some hiccups. Physical properties influence water management. Chemical properties influence fertility management, but the grower controls them all if they do it the correct way. All right. So I know I went over my time, Shamim. I'm sorry, but I'm also not sorry. I hope that's not too much of a problem, and I'm happy to entertain any questions that you may have.
Yeah, thank you, Professor Jackson. It was a nice presentation, and you know it's fine. Like we are within 1 hour's timeline, and we have some time for the questions. So if you'd like to ask the question, you can probably throw the question through the Q&A, or you can directly unmute yourself and you can ask your question.
Hi, can I ask a question?
Sure, go
Yeah,
ahead.
Are there any like a standard that, for example, I am from North Dakota State University, and we have a lot of people that developing new materials, and they come to us and say, "Oh, can you try our new biomaterials?" Da da da. But of course, because they're new, we want to compare with the current commercial, by substrates, let's say. Are there any standard we can compare them so they're not, out of the loop?
that's a really good question, and I too get many of those same requests.
Mm-hmm.
I do not know of a standard in place.
Mm-hmm.
What I do when I'm testing new materials is, first of all, I measure their properties, what's their
Mm-hmm.
particle size and what's their water airspace, and then I see how close they are to a quote unquote standard or traditional peat perlite or peat coconut mix. And
Mm-hmm.
that's a good starting point. And then
Mm-hmm.
when you start to grow plants or irrigation, fertility, whatever you're looking at, I
Mm-hmm.
always start by growing them the same. But then I
Mm-hmm.
never trust those data because I
Mm-hmm.
go back and then grow each one, the new mix and the
Mm-hmm.
traditional, independently based on what it needs. And then
Mm-hmm.
that's when you can really get an idea for the potential of a new material. And then we
Mm-hmm.
look There's some phytotoxicity screening tests that are pretty simple, and I can share that with you. Just send me an email. And there's also ways of looking at degradation and is it stable enough of a material to grow whatever crop you're testing.
Oh, okay. Great. Well, thank you. That
You're
was
welcome.
really helpful. Yeah.
Any other question? Okay, I have a question, Professor Jackson. Thank you again for your presentation. So when you mentioned that like usually for substrate, it's better to kind of put the coarse one at the bottom and a little bit finer one at the top. Is that like help to kind of benefit in terms of the drainage of the water, or is beside this, what could be the other benefit to kind of having that recommendation?
Yeah, so a couple of things. First of all, having coarser material on the bottom of a container and a finer particle size on top does not improve drainage, okay? Because it's kind of like with house plants, if people put rocks or gravel in the bottom of the pot thinking it improves drainage, it does the opposite. Because what it does is it just moves the water, the perch water, higher in the container, and more of the volume of the top is now saturated with less substrate with air. So what it does, it focuses the water and nutrition at the top where the young plant is growing, so it's more efficient, but the bottom has a lot more pore space, a lot more air. And then some of the work that Jeb Fields has done has shown roots really enjoy that high porosity airspace at the bottom. So it's just shifting the water and nutrient efficiency up, and then the bottom is more for just root development.
Okay, I see. Thank you.